Hello dear students. So I, Vikas Agarwal, am here to do the next session and the last session of magnetic effects of current in the B2A series. So let's get started everyone. So we discussed about the force on a current carrying wire, okay, in the previous session. Okay, today we are going to talk about what we call as Faraday's law. Okay, so Faraday discovered something amazing, okay, regarding magnetic field. So we are going to talk about that. Okay, so what did Faraday discover? So guys, suppose there is a magnetic field. Okay, for example, assume that this is a magnet, this is the north pole of the magnet, and we know that the magnetic field lines would be going like this. Okay, it would be going like this, okay, and then like this. Okay, and these are making closed loops, you know, they are coming back and they are entering into the south pole. Okay, so we know that the situation is like this. Okay, now what he discovered, what Faraday discovered was that suppose we are holding a metallic ring here. Let's say we are holding a metallic ring here such that some magnetic lines or magnetic field lines are passing through the metallic ring. Okay, some magnetic field lines are passing through the metallic ring. Then what he noticed was, listen to this very carefully, that if we do anything that can lead to a change in the number of lines passing through the ring, then an EMF will be developed in the ring. That means a current will start flowing because it's a metallic ring. Okay, so a current will develop in the ring and EMF will develop, which will then lead to a current. Okay, so pretty astonishing result. Okay, and a great result, and the result on which the instrument like the dynamo is built, you know, something that can convert mechanical energy into electrical energy. Okay, so what is the concept? The number of field lines passing through the metallic ring, if it changes, mind you student, change is the keyword here. Okay, if it is not changing, it is passing but it is not changing, then there would be no EMF. It is the change that needs to happen. So if we are holding the magnet here, if we are holding the ring like this and we are not doing anything, okay, we are not shifting the magnet anywhere, we are not shifting the ring anywhere, or we are shifting them together such that the same number of lines continue to pass through the metallic ring, in that case there will not be any EMF. The number of field lines need to change. That is the keyword. And how can it change? So one of the way is that you are, you know, shifting the ring along the axis, like you are getting it away, you are bringing it close. In both the scenarios, so long as you keep the ring moving, you will find that a current is flowing in the ring. That means an EMF is generated in the ring. Okay, and what if instead of moving the ring, suppose we begin to move the magnet? Okay, then what? Then also you will see that there is an EMF developed in the ring, and that EMF is leading to a current. Okay, so Faraday law states that whenever there is a change in the magnetic flux. Okay, now what is magnetic flux? I did not talk about what magnetic flux is. So basically it is a parameter, or it is a quantity which is proportional to the number of field lines passing through a chosen surface. Okay, so as of now you can just interpret it to be something which has got to do with the number of field lines passing, okay, like which is proportional to the number of field lines. In once you have drawn a magnetic field, once you have represented a magnetic field by drawing the certain number of field lines, if you find that you are doing any change that is leading to a change in the number of field lines passing through a loop, then it will lead to an EMF in the loop. So in this case, you know, taking it away, bringing it closer, taking the magnet away, bringing it closer, moving them up and down, all these scenarios will result in an EMF. Let me ask you something, you know, let me ask you a situation which I haven't spoken about. What if I start turning this ring? What if I start changing the plane of the ring? Right now the ring is like this. What if I change it like this? What if I rotate it by 90 degrees? So will that lead to a change in the magnetic field, in the magnetic flux? Yes. So there will be an EMF. So if we start rotating this ring like this, you know, if we start rotating this ring about a vertical diameter like this, okay, then also there will be an EMF generated in the ring. Okay, so That's what Faraday's law says. Okay, I'll reiterate it. In fact, I will write it down that whenever, okay, Faraday law says that whenever there is a change, okay, there is a change in magnetic flux. Okay, wherever there is a change in magnetic flux. What is magnetic flux is something that I will describe in a short while. Okay, whenever there is a change in magnetic flux passing through a conducting loop, an EMF is developed in the loop. Okay, now that's not the complete story, guys. That's half the story. Okay, I have not told you Faraday's law completely yet, but this is the first idea that you need to have. Now, this idea is devoid of mathematics. It only talks about a phenomena that is happening. As of now, I have not included any mathematical aspect in it. For example, what could be the mathematical aspect? So, we can talk about how much EMF will be generated. Will it be 5 volt? Will it be 10 volt? What are the factors on which this EMF will depend? Okay, so can we write the numerical value of this? So this is the second part of the Faraday's law. So I'm trying to explain Faraday law to you in parts. He gave a single statement that comprised of everything, but I am breaking it down into 2 parts so that it's easier for you to understand. So first you have to get hold of this idea that whenever there is a change in magnetic flux passing through a conducting loop, an EMF is developed in the loop. Okay. How much is this EMF is something that we will talk about in a short while. Okay. Now, if this idea is okay to you, then let me talk about the next idea, that what is magnetic flux. Okay, what is magnetic flux? So again, before we go into the mathematics, I think it is imperative that you understand, like you get a feel of what magnetic flux is. We generally denote this quantity with a symbol phi. Okay, what is this happening? Okay. We denote this quantity with the symbol phi. Okay, and just a minute, guys. Okay, so magnetic flux, or phi, okay, is a parameter that is proportional to the number of field lines passing through the surface. So when we talk about magnetic flux, we talk about a magnetic flux through a surface. Okay, so magnetic flux, let me mention it here, through a surface, so, or through an area. Okay, so it is a parameter which is proportional to the number of field lines passing through the surface. Okay, now, so if there is ever a situation in which the number of field line is changing, that will lead to a change in flux. Okay, magnetic flux. Is there a mathematical way to write it? Mathematical flux? Yes, there is. Let me explain it to you, and let me explain it by giving you some examples. Okay, and then I will give you a general formula. So let's say this is a rectangular surface with area A. Okay, and the magnetic field is exist in this region of space somewhat like this, you know, which basically means that the magnetic field lines are perpendicular to this, perpendicular to the plane of this rectangle. Okay, so let's say this is the scenario. Okay, so this is a surface which is kept in a region of magnetic field, and the magnetic field lines are penetrating the surface normally. Okay, that means they are striking the surface perpendicularly, means I intend to show that all these angles, they are 90 degree. Okay, all these angles, they are 90 degree. Okay, Now in such a case, if the magnitude of magnetic field, like if this is B, this is A, then flux is described as B into A. This is the amount of flux passing through the surface. It is B into A, magnetic field into area. Remember, this is the situation when the field line is perpendicular to the surface. Okay, then that is the situation. Or you can say when the field lines are parallel to the normal drawn on the surface. See, if I try to draw a normal to the surface, we will draw an arrow like this. Okay, of course you can draw the arrow on the opposite side also. I am deliberately choosing an arrow which is in the direction of magnetic field. So this is the direction of a normal. Normal means perpendicular. So it is the direction of a normal drawn on the surface. So whenever magnetic field is parallel to the normal, then the flux is given by BA. Actual formula, the real formula is B dot A, or you can say it is BA cos theta. Now theta is what angle? Theta is the angle between the normal and the magnetic field lines. Okay, in this situation, can you tell me what is the value of theta? Now, if you are thinking about 0, then you are right. The angle between magnetic field and theta is indeed 0, and cos 0 is 1, and therefore we are getting only B into A. Okay, so for a planar surface, it is very simple, B into A. If the magnetic field lines are parallel to the normal or drawn to the surface. Okay, now what if it is not parallel? Then what? So let me first take another extreme situation. This was one of the extreme situation. Let me take another extreme situation. That would be this. You know, suppose the rectangle is in the plane of this board, okay, in which I'm writing. Okay, and the magnetic field lines are like this. Now, do you see any field line penetrating this area? Do you believe that magnetic any field line is penetrating this area? If you are saying no, then you are right. What is happening here is that the flux is 0, and if you use the formula, if you use this formula, you will be able to understand why it is 0. We will write BA into cos theta. Now understand that the normal to this plane is like this. Okay, the normal to this plane is coming out of the screen, and these green lines are like this. So the angle between these two is 90 degree. The angle is 90 degree, and therefore cos 90 becomes 0. So the flux in this situation is 0. Okay, so that is how we write the flux. Okay, that is how we write the flux. So whenever flux changes, EMF is induced. Okay, this is the part of Faraday law that I am telling you right now. Let me also give you an example. You know, let's try one example also. This time a little bit, a teeny tiny bit difficult one. Okay, so suppose there is a surface, slanted surface like this. Okay, there is a slanted surface like this, and I'm drawing something more just to indicate that the kind of figure. So let's say this angle is let's say 60 degree. Okay, this angle is 60 degree. I hope you are able to understand the situation that I've drawn. I've drawn an inclined plane. Okay, this is the vertical face of the inclined plane. This is the vertical face of the inclined plane. Okay, and I hope the figure is clear, everyone. Okay, so let's say that this length, okay, this length is L. Is it visible? Yeah. Okay, and let's say this length is A, and let's say this vertical length is B. Okay, so you know, this is B, this is A, this is L. This length is not needed. If you want to give it a name, let's say this is D, just in case if you. So I think I have given you all the lengths that I have used in this figure. I've given you all the lengths. Now suppose this figure or this you know, situation is in a magnetic field. Okay, suppose it is in a magnetic field. Are you able to understand what I'm trying to depict? Okay, these are magnetic field lines. So are you able to realize that the slanted surface is getting pierced by the magnetic field lines, and even this vertical surface is getting pierced? Are you able to judge that or not? So let me first talk about the vertical surface. So this is the vertical surface. Okay, magnetic field lines are crossing this surface, and can I say that the magnetic field line, they are parallel to the normal drawn on this surface. They are parallel to the normal drawn on this surface. So the flux through the vertical surface would be B into area. Area would be A into B. Cos 0 is 1. See, The area, this area would be A into B. Okay. Now, suppose if I talk about the slanted surface, so my first thing is that, can you tell me the area of the slanted surface? Like, how much is the area of the slanted surface? Area of the slanted surface. So the slanted surface is still a rectangle with this length as A and this length as L. Okay. So the area of the slanted surface would be A into L, and the normal drawn on the slanted surface would be like this. Are you able to judge this or not? This angle being 90 degrees. So the normal drawn on the slanted surface would be like this. And if we are looking from the side, like if we are looking somewhere from here, like if this is my eye, okay, if this is my eye, we will see only this triangle. The entire other figure will be hidden from us, and we will look at the triangle like this. This angle is 60 degree. The normal will be like this. This is the slanted rectangle. This is the vertical rectangle, and the magnetic field lines will appear like this. Okay, now if I ask you that what is the flux passing through the slanted surface, okay, what will you say? The flux passing through the slanted surface, okay, how much is that? That would be B into AL into cos of angle between this vector, and let's say B vector. Okay, so just for my understanding, if I consider B in the opposite direction, this angle, this will become 60, this will become 30 degree. So we will get cos of 30. Okay, so we will get cos of 30. So this will become BAL root 3 by 2. I'm actually interested in mod of this, so I'm not concerned whether I'm getting a 30 or a 150. The actual angle between the area vector and the magnetic field vector is 150 degree, but cos 150, cos 30, magnitude wise they are same, so I'm okay. So this is the answer that you will getting. And now there is an important thing to notice, guys. What is this L root 3 by 2? Like, is it L sine 30? Like, this length was L, okay, this length was L, so this will become L sine 30, so L sine 60. So in other words, this is nothing but B, so we do get from the formula that the flux passing through the slanted surface is the same as the flux passing through the vertical surface, and that's not a coincidence. Every line which is crossing this slanted surface, the same line is also crossing this vertical surface, and we said that flux is something which is proportional to the number of field lines. So because same number of field line passes through both the surface, the flux ought to be same. It is same. Okay, so this is how we can calculate flux. Of course, this was a bit too difficult for an NSEJS student, so don't worry about this. Okay, if you understood this much part, not this much, this is, you understood this, if you understood that how to write flux, okay, then we are good right now. Now we'll continue about the Faraday's law. So Faraday's law told us that if the flux changes, then EMF is induced. Now Faraday law, continuing Faraday law. Okay, the induced EMF, now I'm talking about the math, it is equal to the rate of change of magnetic flux. Now guys, if you have done the basic mathematics lectures on this channel, then you would know that whenever we talk about rate of change, okay, there are two ways to talk about it. One is the average rate, okay, and the other one is the instantaneous rate. So we can talk about the average EMF, that will be change in flux divided by change in time. I'll consider the magnitude of this. And if we talk about the instantaneous, EMF, okay, then that would be given by d phi by dt. Okay, it would be given by d phi by dt. So this would be the EMF induced. Let me show an example to you. Like, let me show the mathematical aspect of it. So suppose this is a square frame of area 2 meters square, okay, and it has got a resistance in it which is, let's say, 10 ohm, okay, and no other resistance is present anywhere in the circuit, okay, and suppose there was a magnetic field in space like this. Okay, there was a magnetic field, and this magnetic field was, let's say, 2 Tesla. Okay, so there was a rectangular loop made up of metal, having a resistance 10 ohm, and there was a magnetic field 2 Tesla. Area is given to us. Now we have been told that the magnetic field is gradually diminishing and then it becomes zero. It is diminishing, it becomes zero. So are we expecting any current to flow in this loop? So you try to answer this question, everyone. First, you try to answer this question, that are we expecting any current? Because there is a magnetic field, some magnetic field lines are passing through the loop. So when these field lines are changing, do you expect an EMF to develop in the loop? You should. And because there is an EMF, because there is a it's a conducting loop, it has some resistance in it, but otherwise like the path is complete. So there will be a current in this loop, okay, and that current will be given by induced EMF divided by the resistance. So we have to first talk about the induced EMF. So right now the flux is there, like magnetic field is there, area is there, and we can see that the magnetic field line is along the normal. Okay, so the initial flux was 4, the final flux would be 0. So change in flux is this. Okay, the initial flux is 2 into 2, that is 4 Tesla meter square. The final flux would be 0 because the question says that the B diminishes to 0. Okay, so final minus initial divided by the time taken. Now the question also tells us that it becomes 0 in a time span of, let's say, 4 seconds, just let's say. So I'll write it here that B diminishes to 0 gradually. In a time span of 4 seconds. Okay, so we will divide it with 4. Okay, so it will become 1 volt. So 1 volt is the EMF. Now you know the EMF, you will divide it with resistance, you will get the current. So a current of 0.1 ampere will flow in this circuit. Getting this? A current of 0.1 ampere will flow in this circuit. Now if there is already a question buzzing in your brain that, sir, what will be the direction of the current? Will it be clockwise or will it be anti-clockwise? Then that's a very, very valid question, guys. That's actually a valid question, and to address this question we have another law which is called as Lenz's law. Okay, so we'll talk about that in a short while, but first let's understand the Faraday's law. So Faraday's law tells us that how much current will flow. So the answer would be, in this case, it would be 0.1 ampere. I hope you are getting this. Okay, so 0.1 ampere current will flow. Okay, now if you are good with this, let me now talk about Lenz's law. So what does Lenz's law says? So Lenz's law says that the current that will develop, okay, it will develop in such a manner that it can oppose the reason of its own production. Okay, so the induced current or the induced EMF will have a direction such that it can oppose its own production. Of course, that will be unsuccessful. It will not be able to successfully oppose its own production. It will be produced, but it will try to. What do I mean by that? So guys, the reason for the EMF induction or the reason for the current development in this was that the inward going magnetic field lines, they were decreasing. The count of the inward going field lines was decreasing. So the current will try to increase the inward going field lines by giving us a clockwise current. You remember that clockwise current produces an inward field in a loop. It looks like a south pole. A clockwise loop looks like a south pole of a magnet. So the current will be clockwise so that the number of field lines, the number of inward field lines which are decreasing, the current may compensate that decrease. Of course, it will not be able to successfully do that, because if it does cancel that effect successfully, then the current will not be produced because the flux is not changing now. Okay, so Lenz's law says, that the direction of the EMF is such that it can oppose its own reason of production, or it can oppose the reason of its own production. Okay, and this is actually a great thing. That's actually a great law. It helps you in so many ways. I'll tell you how. Like let me try to give you some examples on Lenz's law. Okay, for example, suppose this is a loop. Okay, now suppose this is a loop and this is the magnet. Okay, and this end, the end away from you guys. Okay, this is North Pole. So if I take the North Pole closer to the loop, okay, then the inward field lines would be increasing. So to oppose that, we will get an anti-clockwise current. You know, if we are bringing the magnet closer with the north pole. Okay, let me draw alternative view. Okay, this view may not be very good to explain. So let me draw an alternative view. So suppose this is our, this is a loop. Okay, this is a loop, and let's say, let me draw a plus sign here to set some context. Okay, and now let's say this is a magnet. Okay, and this is the north pole of the magnet. Okay, I'm not drawing the field lines. I'm not drawing the field lines. So if we bring this magnet closer, okay, if we bring this magnet closer, then a person here will witness what? Okay, if we bring this magnet closer, then, okay, let me draw the field lines. Okay, in this position, the field lines would look somewhat like this. Okay, so if we bring the magnet closer, the flux coming towards the eye of this person will increase. Okay, so this person will see a clockwise current. This person will see a clockwise current. Okay, so that the outward field lines can be compensated by the inward field lines that will be developed due to this clockwise current. So this person will see a clockwise current. In other words, this person will, will see south pole of a magnet, which also means that this side will be a north pole of the magnet, and therefore this loop will repel the magnet. So you try to bring the magnet close, the loop will develop a current in itself, and then it will start repelling the magnet. On the other hand, if you try to take the magnet away, then the loop will start attracting it. So you try to bring it close, loop will repel. You try to take it away, loop will attract. You try to keep it stationary, loop will do nothing. Okay, so let's understand this. When you're trying to take it away, the flux which is coming towards the eye of the observer is decreasing. So the loop will develop a current which can increase this flux. Now this is outward flux for him. So he will then witness a north pole here, and the current will become anti-clockwise. So this will become south pole. It will start attracting the magnet. Getting it? So whatever is the reason, okay, because of which the EMF is produced, okay, the EMF will oppose that reason. Let me give you some more example. Okay, let me give you some more example. So suppose we prepared an arrangement, this is a loop, and then we have attached a resistance here like this. Okay, this is the axis of the loop. Okay, and we are keeping a magnet here. This is north pole of the magnet. Okay, now you have to tell me, you have to think about that. If there is a current in this loop, will it flow from X to Y or will it flow from Y to X? So if we bring the magnet close, okay, then this will try to repel the magnet. So this side will act as the north pole. Okay, this side. So if this side has to act as a north pole, then looking from this side, we will be seeing a clockwise current. And if the current here will be clockwise, then the current direction will be Y to X. Are you getting it? If we bring the magnet close, the current will be Y to X. If we bring the magnet away, the current will be X to Y. So long as you move the magnet, till that period, you will observe a current in the resistance. Okay, let me give you another example. Suppose this is a metallic ring. Okay, suppose this is a metallic ring which is fixed. Okay, and things can pass through it, and there is a magnet. And you released this magnet and you are allowing it to fall through the ring. Okay, you are allowing it to fall through the ring. This is a metallic ring. Okay, this is a metallic ring. So what will happen is that when this magnet begins to fall, the flux through this ring changes. Okay, the flux through this ring begins to change, and it will, the reason of that change is the falling magnet. So it will try to stop that fall. Meaning that normally you would expect it to fall with an acceleration which is equal to g, but right now the acceleration would be less than g. Why? Because as soon as it starts falling, some current will be developed here, and that current will definitely try to stop its downward motion. So it will push it upward. Okay, but it will not be successful in cancelling out the motion. So it will come down, but because of the upward force, the acceleration is no longer g, it is less than g. Now once it has passed through the magnet, Then also the flux through the ring is changing. The reason for the change is the falling magnet. So this ring will try to prevent the fall of the magnet by applying an upward force, that is by applying a attractive force. Now when the magnet was falling from the top, the force was repulsive and therefore upward. When it is going downward, then the force is attractive and therefore upward. So in both the cases the force is upward, and therefore in both the locations the acceleration will be less than g. Okay, so the Faraday's law allows us to find out the direction in which the EMF will be developed. Okay, and Faraday's law and Lenz law allows us the direction, and combining them we write the induced EMF as minus d phi by dt. The minus sign indicates that the EMF will it will try to oppose the rate of change of flux. If it is trying to increase, the EMF will try to decrease it. If it is trying to decrease, then the EMF will try to increase it. All right, students. So with that note, guys, I will end today's session, and we are done with this chapter now. We'll start a new chapter in our next session. I hope you enjoyed these sessions, guys. Remember, guys, that these sessions you can always watch by slowing down the pace, by pausing the video, by thinking over the statements that I'm giving you. And if I'm asking you to imagine a direction, you can pause the video and then you can imagine the direction, and then you can continue the video. This is the way you should try to learn it. Okay, and I hope you are learning from these sessions. Take care, students, and you'll see me in the next session of B2A series. Bye-bye.